Hello everyone. This video we will go over problem of the week number 4 for the summer session. Number 1A, you can do it from scratch. From scratch I mean take the limit directly, or you can use a result from a calculus 1 that says the following, and this is one of the most useful limits to remember throughout your mathematical career, that the limit as n goes to infinity 1 plus a over n to the n power is equals to e to the a. To convince yourself about this result, actually you just have to use L'Hopital's rule, and you'll end up with this result. But this is very important. You should definitely memorize this result. All right, so if we use this formula, so the limit as k goes to infinity of 1 minus 3 over k to the k. So notice here that the value for a is equals to negative 3. So therefore, if we use this formula, or this limit, this just will be e to the negative 3, which is finite. So therefore, the sequence converges. Now you have to be very careful to understand the difference between a sequence and a series. For a sequence, as long as the limit is not infinity or it doesn't oscillate, then you are good. So doesn't matter if it is 1, 0, as long as it's not infinity and it's not oscillating between two different numbers, the sequence converge. Doesn't mean the series converges, but the sequence does. All right, part B, if we take the limit as k goes to infinity, a tangent inverse of a over k, this is the same thing as tangent inverse of the limit as k goes to infinity of a over k, which is the same thing as tangent inverse of the limit of this, which is 0, and tangent inverse of 0 is 0. Again, these are all limits from calculus 1, so I highly recommend you to review this. Right, for part C, if we take the limit as k goes to infinity of sine k over k, notice that sine is oscillating between minus 1 and 1, so it keeps going from negative to positive. But since this is going to infinity, the whole thing is going to go to 0. So in this case, this is equals to 0, which is less than infinity, so therefore it's converging. So it's this one. Remember, the value doesn't matter for a sequence as long as it's not infinity or keeps oscillating. Again, here, this is oscillating from minus 1 to 1 for this part, but the graph will look like this technically. Could be doing that, but eventually it will go to 0. So it is converging to 0. So converges to 0. Okay. Part D, here you can see the cosine of k pi, where remember k is always supposed to be it's an integer, which means it can be positive or negative. But in this case, k is going to infinity, which means that you're going to have cosine of pi, 2 pi, 3 pi, 4 pi, and so forth. So the values for cosine are going to be 1 minus 1, 1 minus 1, and so forth. So the limit doesn't set up to a specific value. So it will keep oscillating all the time. So it doesn't set to a specific value. So therefore the limit doesn't exist. So therefore the limit as k goes to infinity of cosine k pi excuse me, doesn't exist. So that implies that AK is divergent. That's it. Okay, now let's move on to number two. In number two, now we're talking about series. And remember, a series is the sum of all the values of the sequence. So a series and a sequence are not the same thing. So you have to be very careful with that. And for the series to be convergent, that means when you do the whole sum is less than infinity. So this will be convergent. And if the sum is equals to infinity, then it will be divergent. Okay. And there are several tests. The most basic one is the divergence test. And then the next one you've seen in this so far is the integral test. For this one, you can use either or. But let's go with the divergence test, which will remind you of, again, limits from calculus 1. So here, remember, this is AK. Now the limit as k goes to infinity, k over the square root of k squared plus 4. Notice, and again, this is just a review from calculus 1, that k squared plus 4 is the same thing as k squared times 1 plus 4 over k squared. So you take the square root, this will just give you the absolute value of k times the square root of 1 plus 4 over k squared. Why is that important? Because then here we have the limit as k goes to infinity of k over 1 plus 4 over k squared. Again, this is a limit from calculus 1. Here we use a k because this is the absolute value. Since k is going to positive infinity, this just becomes k. Here the k's will cancel. So therefore this will be equals to 1 over the square root of 1 plus 0, which is 1. Now, since the limit is not equals to 0, then by divergence theorem, the series is divergent. And that's it. In this question, you can also use the integral test. And technically, all you have to do is integrate this x over x squared plus 4dx. And you will see that the integral is equals to infinity, which will show you that it's divergent too. So you can do either or for this particular problem. Okay, let's move to part B. Here, notice that if we try to use the divergence theorem, the limit as k goes to infinity of 10 over k squared plus 4, this is equals to 0. Remember, if the limit is not equals to 0, then by the divergence theorem, then the series is automatically divergent. But the opposite is not true. If the limit is 0, it doesn't mean that it's convergent. It pretty much just means that now you actually have to find another test to decide whether it's convergent or divergent. In this particular case, the method we have seen so far, the method we've seen so far, the best one is the integral test. So therefore, if we integrate from 0 to infinity of 10 over x squared plus 4 dx, you can take the 10 out, so this will be the integral of dx over x squared plus 4 from 0 to infinity. So then it will be 10 times 1/4 tangent inverse of x over 2 from 0 to infinity, and this should be 2, not 4. Because remember, this is x squared plus 2 squared. So then this is phi tangent inverse of x over 2 from 0 to infinity. Remember, tangent inverse of infinity is pi over 2, and tangent inverse of 0 is 0. So this is 5 pi over 2, which is less than finite. So that implies that is convergent by the integral test. That's it. Okay, in part C, there is actually a typo, and that's why some people got confused. So that is my fault. There is one part missing here. So the actual sequence should be like this: plus 116, plus 164, and so forth. So here, the easiest way to determine the convergence is to realize right away that this is just a geometric series where the value for r is 1/4. Therefore, you can rewrite this as the sum from k equals to 0 to infinity of 4 times 1/4 to the k power. Now, since the absolute value for r is less than 1, then that implies that it is convergent by the geometric series. Now, since we are going to be using convergent and divergent a lot from now on, just to be a little bit lazy, this is going to mean convergent. That's just me being lazy to write faster, and this is going to be divergent. All right, so for part 1D, this looks very, very similar to 1D, but not quite. Remember, from there, the limit as n goes to infinity of 1 plus a over n to the n power is equals to e to the 8. So this is not quite the same because this is a square and this is not a square. But I told you that this result came from using L'Hopital's rule. So we're going to do that here. So let y equals to 1 minus 1 over x squared. Therefore, ln y is equals to x squared times ln of 1 minus 1 over x. Notice that you can also rewrite this as ln of x plus x minus 1 over x. Also, notice that you can rewrite this as ln of x minus 1 over x, like I just told you, but the important part is this is the same thing as 1 over x squared. Okay, so this will be the numerator, this is the denominator. Then if we take the limit, so the limit as x goes to infinity, it will give you ln of 1 on the top, which is 0, and in the bottom is 1 over infinity, which is 0. Therefore, you can use L'Hopital's rule. So you take the derivative of the top. Also notice that this is the same thing as ln of x minus 1 minus ln of x. Therefore, this is the same thing as the limit as n goes to infinity. On the top, this is going to be 1 over x minus 1 minus 1 over x. You take the derivative, and on the bottom is going to be minus 2 over x cubed. Now, if we do a little bit of algebra, you can check that this actually simplifies to 1 over x minus 1 times x. So therefore, this will be the limit as x goes to infinity of x cubed over minus 2 x minus 1 times x, which is equals to minus infinity. So that implies that ln of y is minus infinity, but remember, we don't want ln of y, we want y. So that implies that y is equals to e to the minus infinity. Remember, all of this is in limit terms, which is equals to 0. All right, so now since the limit is 0, we know that the series is since the limit is not equals to 0, therefore the convergence can still go either way. So we will need to have a different test. Now, the easiest test to do this is actually the ratio and the rule test, which we haven't covered yet, but we will do in the next participation. And because this is equals to 0, which is less than 1, you'll see that when we go to the next section, this is actually convergent. All right, finally, number 4. Question 3 says the following, according to Pikachu, the following series is convergent by the divergence test since the limit is equals to 0. Is he right? And the answer is no, like I just explained right now. If the limit as k goes to infinity or n goes to infinity, so there should be also k, of ak is equals to 0. If the limit is not equals to 0, then that implies that it's divergent. But if the limit as k goes to infinity of ak is equals to 0, it doesn't mean that it's like convergent. It doesn't mean that it is convergent. You still need to check, and that's what I mentioned in this case. So here the limit was 0, so that doesn't mean anything yet. You still have to check. And if we use the ratio test, which is the easiest one in this particular case, the limit is 0, which is less than 1, so that's why this will be convergent. And the particular problem we have here, this is actually divergent. So this one is actually divergent since this is a p-series where p is equals to 9 over 10, which is less than 1.